Welcome back to Sulekha physics classes. It is the most easiest way to learn all the concept of physics through this class. Hope you all are doing well. Now today I am going to start one short revision of chapter 2, that is electrostatic potential and capacitance. This chapter is very large. It is divided into two parts, electrostatic potential and capacitance, but we'll cover all the topics, right? No portion is deleted from this chapter. So I will cover each and every topic, but still there are some important topics like electric potential due to a point charge, due to an electric dipole, electrostatic shielding, equipotential surface, potential energy for a system of two charges, potential energy or work done by the dipole when it is placed in an external electric field, and in capacitor expression for capacitance for a parallel plate capacitor, energy is stored in a parallel plate capacitor, what happens when dielectric is introduced between the plates of a parallel plate capacitor, right? So we'll focus more on these topics, right? Okay, so let us start. Quick revision of this chapter, electrostatic potential and capacitance. As the name suggests, electrostatic potential. First part is electrostatic potential and second half of this chapter is capacitance. So what is electrostatic potential? Before this, you must know about electrostatic potential difference or electric potential difference. You can say same thing, right? Suppose there is a charge Q and you know that around this charge there is a region, that region is called electric field, right? When you put any test charge, positive test charge in this region, in this electric field, what happens? That positive test charge experiences some force, and due to that force it moves. Suppose this is a positive test charge and the force acts on this positive test charge in this direction. Now if you want to move this discharge from this position B to position A, but force is in this direction towards right and you have to move this charge towards left. So what you have to do? You have to apply some force in the opposite direction, external force, or you have to do some work against work done by the electric field. In this direction, work is done by the electric field. So you have to apply force in the direction opposite to that one, work done by the electric field, W external. And how much work is done to move a charge from this position B to position A? That is called electric potential difference, right? You can define in this way: work done in moving a test charge from one point to another point in electric field, or you can say against electrostatic force of attraction, right? So you can write potential difference between A and B is this positive test charge moves from B to A. So potential at suppose A position is suppose VA, right? And potential at B position suppose VB, and you know electric field is this direction, right now? So potential decreases in the direction of electric field. It means potential at B is less than potential at A. So move a test charge from B to A, it means VA minus VB. This is potential difference, and this potential difference to move a test charge from B to A, VA minus VB is equal to work done in moving a charge from B to A, or you can write W external. This W external is equal to minus of W electric field, because work done by the electric field is in this direction, W external is in this direction, and W this B to A, right, is in opposite direction. So this VA minus VV is potential difference between point A and B, and it is given by work done in moving a test charge Q0 from position 1 to position 2, right? So its formula becomes this one. Okay, I am using red marker so that it becomes clear. Potential difference is this one. In moving a test charge from B to A, VA minus VV equal to W external by Q0. Okay, its SI unit. SI unit is W is in joule and Q is in coulomb. So you can write joule per coulomb or volt also. This is the SI unit of potential difference, and this potential is a scalar quantity, right? I am writing something here. It is very important. Potential decreases in the direction of electric field. I will prove this one, how potential decreases in the direction of electric field. But you must remember this point, that potential decreases in the direction of electric field, right? Okay, one more thing, dimensional formula. What is the dimensional formula for this potential difference? Work done is what? Force into distance. So force into distance is, force is MA, so ML square, right? T minus 2 M, force, what is the formula, dimensional formula for force? ML T minus 2, right? Force into distance, distance is L, right? This is dimensional formula for force into distance. M, so it becomes M L square T minus 2. Right now, work done. This is work done. And in the denominator, coulomb. Q is what? Q is I into T. So I is in ampere and T is in T. So the final formula becomes this one, right? M L square T minus 3 A minus 1. This is the dimensional formula for electrostatic potential difference, right? Now, next one is electrostatic potential. This is potential difference between 2 points. But now you have to find electrostatic potential at point A, suppose, or point B. So how you write this one? So for this, we assume that the second point is at infinity. Suppose here point B is here. But now suppose B point is at infinity and test charge is placed at that point. Now work done in moving a test charge from this point infinity to point A is nothing but electric potential at point A. So you can write from infinity to A means VA minus V infinity equal to work done from infinity to A by Q0. This is W external by Q0, and you know potential decreases as distance increases. It becomes 0 at infinity. So V infinity is 0, right? So this becomes VA, or simply write V. This is electrostatic potential at point A, right? Work done in moving a test charge Q0 from infinity to point A. You can write this work done in bringing a unit positive test charge from infinity to the point where you want to find potential, right? Suppose at point A, so this VA, or you can write simply V, potential at point A is work done by Q0, right? Again, SI unit is same as that of potential difference, that is volt or joule. Or you can also write work done is force into distance. So Newton meter per coulomb. This is other unit, and it is one more important thing. It is path independent. Potential is path independent. It does not depends on path, right? So hope this topic is clear. What do you mean by electric potential difference and electric potential, right? Now, next topic is what is the formula for potential at any point due to this test charge in terms of charge and distance at which potential is to be determined, right? So please take a screenshot of this. Now, electrostatic potential due to a point charge. Suppose there is a plus Q charge, point charge at this point, right? Now you have to find potential at this point P, which is at distance R from this charge plus Q, right? So to find potential at point P, we first suppose that any test charge plus Q is placed at point B, and you know that due to this charge there is electric field, and this test charge experiences some force due to electric field by this charge, right? And the force experienced by this test charge is in this direction, right? Now to move this test charge from B to A, you have to apply some external force, you have to do some work. So you can write in this way: first, how much force acting on test charge Q0. This force is equal to, suppose this test charge is at a distance x from this charge. So separation is x, two charges Q and Q0. So force experienced by this test charge is F equal to K Q0 by x square. Now we have to move this test charge from B to A. So the extra amount, suppose this distance from B to A, small distance dx, and the small amount of work to move a test charge from this point B to A is given by dw equal to F dot dx. Now dx is in this direction, F is in this direction, there is angle of 180 degree, right? So F dx cos 180, it means minus F dx. And it's clear, na? Force is in this direction, you have to apply external force in this direction, opposite direction. So external work done is minus F dx, right? Or you put the value of F from this equation 1, it becomes dw equal to minus K Q0 by x square dx. This is a small amount of work done from B to A. Now we have to find potential at P. So we assume other point is at infinity. Suppose that the test charge Q is present at infinity. Now amount of work done to move a charge from this infinity to point P is what? W equal to integration of this dw from infinity to point P, and it is a distance r from the charge. So infinity to r, right? So you put the value of dw from this one, minus K Q0 by x square dx, and integration infinity to r. All these terms are constant, K, Q, Q0. You take it outside, minus K, Q, Q0, integration of dx by x square. Now you have to integrate. So you know what is the integration of 1 by x square dx? This is minus 1 by x. Use just this formula. You know na, integration of x to the power n is x to the power n plus 1 by n plus 1. So in this way you find integration of this 1 by x square. It becomes minus 1 by x. Just you remember this one, right? Integration limit is from infinity to r. You take this negative sign outside, negative, negative, positive, K, Q, Q0, and then inside this bracket, first upper limit is r, so you put in place of x, r, 1 by r minus 1 by infinity, and you know 1 by infinity is 0, so this w becomes K, Q, Q0 by r. This is equation number 2, and this is the work done in moving a charge from infinity to point P. It means when you find the potential at point P, that work done by charge Q0, test charge, right? So potential at point P is V equal to W is how much? K Q Q0 by R divided by Q0. This Q0 cancel, it becomes K Q by R. So we get final expression for potential due to a point charge Q at a distance R is V equal to K Q by R, right? It's clear? I think there is no doubt. First, you find small amount of work done moving a charge from B to A. Then you integrate over from infinity to point at which potential is to be determined. Suppose at point P, which is a distance r. And in this case, you get V equal to kq by r. And you know it is a scalar quantity, its SI unit is volt, right? Other unit, there is one other unit, that is electron volt. And you know 1 electron volt equal to 1.6 into 10 to the power minus 19 joule. Must remember this one also. Okay, so take a screenshot of this one. Then we'll move to the next topic, electrostatic potential due to a system of charges. Right? Now, electrostatic potential due to system of charges. We already know that what is the expression for potential due to a single point charge. That potential due to a single point charge is given by kq by r at a distance r. Now here there are number of charges. Suppose q1, q2, q3, there are qn number of charges and their position vectors are r1, r2, r3, rn. Suppose you have to calculate total potential at this point O. So total, you know that potential is a scalar quantity. So total potential at this point O is equal to algebraic sum of potential due to all other charges. So you can write in this way, total potential at point O is V and it is equal to V1. V1 is the potential due to charge 1 plus V2. V2 is the potential due to charge Q2. In this way, you can write. So, total potential is algebraic sum of potential due to all other charges. You know the expression of potential due to single point charge, kq by r. So, potential due to first charge q1 is v1. You can write v1 is kq1 by r1 at a distance r1 plus v2. V2 is kq2 by r2 plus dash dash dash. Potential due to this nth charge qn, kqn by rn. You take k outside, inside the bracket q1 by r1 plus q2 by r2 plus dash 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 qn by rn. So here, if charge is 1, position vector is 1. Charge is 2, position vector is 2. So you can write, this is the sum, summation. So this is symbol for summation qi by ri. And I value for I is first 1, 2 in this way up to nth. So value of I equal to 1 to n and take a outside. So expression for total potential due to a system of charges, n number of charges, it becomes V equal to K is constant summation of Qi by Ri, where I equal to 1 to n. Okay, first you put I equal to 1, Q1 by R1, I equal to 2 plus Q2 by R2, sum of potential due to individual charges. In this way, you calculate total potential when a total large number of charges are present in the system. Some numericals may ask in the examination, so you just remember this one. Please take a screenshot. Then we'll move to the next topic. Next, electrostatic potential due to an electric dipole. You know what is electric dipole? A system of a pair of two equal and opposite charges separated by some distance forms dipole. So here a pair of two charges minus q and plus q separated by a distance 2a, this forms a dipole. Now there are two cases. You have to find electric potential along axial position of the dipole. Axial position means along the line joining the two dipole. Suppose this is a point P and this point P is axial position. You have to find total potential at point P. You know potential is a scalar quantity. So here there are two charges minus q1 plus q. So here total potential at point P is due to the sum of these two charges. Now you have to find potential due to plus q charge and then potential due to minus q charge. As potential is a scalar quantity, you just add these two potential, you get total potential at point P, right? Suppose this dipole is of length 2a. From the center of the dipole, suppose the point at which potential is to be determined is a distance r, right? Now, I want to know the distance of the charge, these two charges to the point P. So, first plus q charge. This distance is r and this one total is a. It means from the center this one is a and total is r. So this distance becomes r minus a. Now distance from minus q charge to the point P. Here it is a, right? And from this one r. The total distance becomes r plus a. Now you know the distance, the value of charge. You can easily calculate potential due to these two charges. So you write it this way. Total potential due to plus q charge is kq and distance is what? R minus a. Right? Now next, potential due to minus q charge. It is a distance. Minus q charge is r plus a. Total potential is V due to minus q charge minus kq by r plus a. Here I have taken negative sign of this charge because potential is a scalar quantity. So you must take negative sign, right? Now total potential at P, as it is a scalar quantity, so total potential due to plus q charge plus potential due to minus q charge. A total potential at point P becomes V equal to, due to plus q charge, kq by r minus a, and due to minus q charge, minus kq by r plus a. You take kq outside common, here LCM, r minus a and r plus a, right? This side becomes in the numerator here r plus a minus here r minus a. Just open the bracket, it becomes r plus a minus r, a minus plus a. It just cancel, r cancel each other, it becomes just twice a. Sorry, here it is twice a. Okay, kq into twice a, and you know q into twice a is what? Dipole moment P, right? P is the dipole moment, q into twice a. So this V becomes, in place of q into 2a, you write dipole moment P, kp by r square minus a square. Now suppose this dipole is of very short length. For short dipole, this distance a is very less in comparison to r. For r greater than a, you just neglect this a square and this potential becomes kp by r square. This is the final expression for potential for short dipole along the axial position. V equal to kp by r square. It's clear that V is inversely proportional to r square. As the distance increases, potential decreases square of that distance, right? In this way, you find electrostatic potential along axial position of electric dipole. Please take a screenshot, and next I will discuss electrostatic potential due to electric dipole along equatorial position. Now along equatorial position, you know equatorial position, perpendicular bisector of the dipole is equatorial position. Suppose this is a point P and this is perpendicular bisector of this dipole. So this point P is equatorial position, this point, every point is equatorial position. Now you have to calculate total potential at point P due to these two charges, right? In the previous, I think along axial position, I have written x by mistake. You just correct it, you write r, okay? So suppose let P be a point at a distance r from the center of this dipole along equatorial position, at which you have to calculate electric potential. So if this distance is r and perpendicular bisector means this one is also a, this one is also a. It means distance to the point P from this plus q charge is under root r square plus a square. Here also distance from the minus q charge is under root r square plus a square. Now distance is this one, charge is this. So potential at point P due to plus q charge is given by kq by under root r square plus a square, and potential due to minus q charge is minus kq by under root r square plus a square. As potential is a scalar quantity, so you just add these two potentials. So total potential at point P is potential due to plus charge plus potential due to minus charge, and you know You write these two values, total potential becomes 0. So it's very easy to calculate total potential along the equatorial position of an electric dipole is always 0, right? So at this point also 0, at this point also, along this equatorial line, total potential is always 0, and this surface is called equipotential surface. I will discuss after this topic what is equipotential surface. Those surface at which electric potential always remains constant. Here at every point on this line total potential is 0, so this surface is also equipotential surface, right? It's clear, it's very easy to calculate. Take a screenshot. Then one more important point, it generally comes in 2 or 3 marks question, relation between electric field and electric potential. Next, relation between electric field and electric potential. This topic is also very important. It may come in generally 2 or 3 marks questions, right? You have to find relation between electric field and electric potential. For this, let's suppose that this is a positive charge Q kept at this point, and suppose there is another charge Q0, test charge, which is kept at position B. Now, due to this positive charge, it experiences some force, and that force is acting in this direction, in the direction of electric field. The electric field due to this positive charge is in this direction, and due to this electric field, this charge experiences some force, and that force is equal to Q0 into E, equation number 1, right? Now, if you want to move this positive test charge from position B to position A, so you have to apply some external force, you have to do some external work done to move this test charge from this position B through a small distance dr to position A, and that small amount of work done is given by F dot dr. Now F is in this direction, okay, and dr is in this direction. Both are in opposite direction, so angle between them is 180 degree. F dr cos 180, and this equal to minus F dr. From this equation, you put the value of F from equation number 1, Q naught E, it becomes dW equal to minus Q naught E dr. From here, you get dW by Q naught equal to minus E dr. Equation number, this is 2, right? Now, by definition, what is potential difference? To move, work done to move a charge, this positive test charge from position B to position A is nothing but potential difference. Okay, so from B to A, it means VA minus VB, small amount of work done dW to move a charge Q0 through a distance dr, right? Now you know potential decreases in the direction of electric field. Electric field is in this direction, right now. So at point A, potential is higher than that of point B. Let us suppose that potential at point A is V, and suppose potential at point B is less than this one by a small amount, V minus dV, right? Now you put these values, VA is V minus this VB is what? V minus dV. So this V minus V cancel, only you get minus minus plus dV. So dV equal to dW by Q naught by definition. This is equation number 3. Okay, right. Now from this equation 2, dW by Q naught is minus E dr. Here dV is dW by Q naught. So from 2 and 3, right now you get dV equal to minus E dr or E equal to minus dV by dr. This is the relation between electric field E and potential difference, this dV, right? E equal to minus dV by dr. It's very important, okay? And what is this negative sign shows? It is also very important for 1 marks question. Negative sign shows that electric field, right, is in the direction of decreasing potential, or you can say this potential difference decreases in the direction of electric field. Any way you can say easily. So just to write, negative sign shows that potential decreases in the direction of electric field. Right? Hope you understood. Okay. Please take a screenshot of this one. After this, we'll move to the next topic, that is equipotential surface. Next, equipotential surface. What do you mean by this surface? I already told you that equipotential surfaces are those which have same potential at every point on that surface, right? So you can define this way: any imaginary surface that has same electric potential at every point on it. Right? Suppose this is a point charge Q and you have to draw equipotential surface for this point charge. You know, due to this positive charge, electric field is in this direction, electric field lines, right now, away from the positive charge. So, at equal distance from this positive charge, potential is same. If you join all these points, you get a spherical shape, right? So this imaginary spherical surface are called equipotential surface. At equal distance, suppose at this point, from this charge, this point, again this surface, at every point potential is same. So this is also equipotential surface. So all these surfaces are equipotential surface, right? Equipotential surface. So you have to draw equipotential surface for point charge like this one. If it is negative charge, you just draw field lines towards the charge, and all these things are same. For point charge, equipotential surface is spherical in shape, right? For uniform electric field also, suppose this is a uniform electric field E, and you have to draw equipotential surface on this uniform electric field. You just draw this plane. This plane shows equipotential surface for uniform electric field, right? There are different properties of this equipotential surface. No work is done on moving a test charge over an equipotential surface. You know, at every point on this equipotential surface, potential is same. So change in potential is what? Between this point and this point, potential same, change in potential is 0. And if change in potential, this delta V is 0, it means work done is 0. So no work is done in moving a test charge over equipotential surface. Second one, electric field lines are always normal to equipotential surface. This one is electric field lines and this one is equipotential surface. That field lines is always normal to this surface. This one is equipotential surface and this is electric field lines. This is equipotential surface. The field lines are always normal to that surface. Third one, two equipotential surfaces never intersect each other. It means suppose there are two equipotential surfaces. This one is one surface, right? And this one is another surface. This has potential V1 and other surface has potential V2. If these two surfaces intersect, then at this point of intersection, it has two potential V1, V2, which is not possible. At one point only one potential is there. So two equipotential surfaces never intersect because at the point of intersection there may be two values of potential, which is not possible. This point is also very, very important. It may come in 1 or 2 marks, right? Why two equipotential surfaces never intersect each other. So these are different properties of equipotential surface. Also one more property is there for field lines very close to each other. Where field lines are very stronger, equipotential surfaces are also very close to each other. The points where field lines are not stronger, it means weaker, at that point equipotential surfaces are farther apart from each other, right? In exams it may come that draw equipotential surface for point charge, then you have to draw like this one, spherical surface. Equipotential surface for uniform electric field like this plane. One more thing, draw equipotential surface for two equal opposite charges for the same charges. Then how you draw? Let us see. First take a screenshot of this one, right? Okay, may I have this one? Hope you have written or taken a screenshot, right? Okay. Equipotential surface for a system of 2 point charges. Right? These 2 point charges may be of same sign or of opposite sign. Suppose there are 2 positive charges plus Q, and here it is also plus Q. You know what type of electric field lines, how you draw electric field lines for these 2 positive charges, right? Yes, field lines are always away from this positive charges, na? Like this one. Yes, here also field lines are always away from this positive charges, like in this way. Now, how you draw equipotential surface? You know, due to point charge, equipotential surface is spherical in shape, but here it is find that this side electric field is more, these field lines are very closer to each other, this side field is less, again this side field is more, this side field is less. So equipotential surface are closer to each other where field lines are strong. So this side, like this one, equipotential surface are closer to each other, this side farther apart from each other, this side closer to each other, this side farther apart from each other. Same, this two also, equipotential surface is like this one. This side, these are closer to each other, and this side they are farther apart from each other. This side they are farther apart from this side, they are closer to each other. In this way, you draw equipotential surface, right? These are equipotential surface. These are equipotential surface, okay? And similarly, you have to draw equipotential surface for 2 equal and opposite charges. One is plus Q and the one is minus Q. How you draw for that one? Suppose this is a positive charge and this one is minus charge. What type of field lines? From positive to negative, na? This side, like this one. These are electric field lines. First you draw electric field lines, okay? Now, here you find that field lines are closer to this side, so a stronger field is at this place and weaker field is to this side. So here equipotential surface are closer to each other to this side, right? Like this one. Here farther apart, here closer to each other, okay? Here farther apart, here closer to each other. These are equipotential surface. This side field lines are strong, so they are nearer to each other. This side they are farther apart. This side nearer to each other, this side they are farther apart. So these are equipotential surface, right? Surface for a pair of equal and opposite charges, okay? So in this way you draw equipotential surface for point charge, uniform electric field, for 2 same like charges, same with positive charge, in the same way negative charge also, only field lines are towards the charge, and for 2 equal opposite charges plus Q and minus Q, field lines are like this one. In case of 2 unlike charges, field lines, equipotential surface are closer to this side and this side farther. In case of 2 like charges, field line equipotential surfaces are closer to this side and they are farther apart from this side, okay? In this way you draw. It's very, very important from examination point of view, okay? Take a screenshot. Next is electric potential energy. What do you mean by electrostatic potential energy? It is work required to bring charges from infinity to that point to form a system of charges, right? And that work done is stored in the form of potential energy of the system. It is denoted by capital U, right? Capital U. You know, potential at any point is what? Work required to bring a charge from infinity to that point, W by Q. Suppose, okay, so this W becomes VQ, and this work is stored as a potential energy in the system, right? And this potential energy U equal to V into Q. And you can also write V equal to U by Q, potential energy per unit test charge. Now in exams it may come that derive expression for potential energy for system of charges, for system of 2 charge, 3 charge, 4 charge, in this way. Now I am going to derive potential energy for a system of 2 charges, right? You want to assemble the 2 charges in the system, then what is the potential energy for a system of 2 charges? For this, suppose charge Q1 is at infinity, right? Suppose the charge Q1 is at infinity. Now you want to bring this charge to a point A. Now the amount of work done in bringing a charge Q1 from infinity to point A is given by W1 equal to Q1 infinity to point A. It means VA minus V infinity. And you know V infinity is what? 0. So this becomes Q1 into VA. Now what is the value for this VA? Potential at point A. There is no charge surrounding this, near this charge. So there is no potential near this charge right now. In this way, here VA you can take equal to 0. No charge is present, no electric field is present surrounding this charge. Okay, so no potential at point A. So in this way, W1 equal to 0. Amount of work done in bringing a charge, particular charge from infinity to a particular point, if there is no any other charge, then that work done is 0. Okay, now charge Q1 is at point A. Now you want to bring another charge from infinity to point B. Suppose Q2 charge. So the amount of work done bringing a charge from infinity to point B is what? W2 equal to Q2 charge from infinity to B. So VB minus V infinity. You know V at infinity is 0. So this becomes Q2 VB. Now this time is VB 0? No. There is a potential at point B due to which charge? This charge Q1. Previously there is no charge near Q1. Now near this Q2 charge there is a charge Q1, there is electric field of Q1, then potential is also there. So you have to find this potential at point B due to charge Q1 is given by K Q1 by distance between the two charges is R12. So you can write VB equal to K Q1 by R12. So W2 equal to, you put these values in this equation Q2, then K Q1 by R12. So in this way, total work done becomes, in bringing these two charges from infinity to form a system of 2 charges, is W1 plus W2. You know W1 is 0 and W2 is K Q1 Q2 by R12. Okay, now this work is stored. I am writing here, please note down. This work is stored as potential energy of system. How many charges? Potential system of 2 charges, right? So you can write U equal to this 0 plus K Q1 Q2 by R12 means K Q1 Q2 by R12. This is potential energy for a system of 2 charges. In this way you can find potential energy for a system of 3 charges also. Potential due to 2 charges are this one. Now you want to bring third charge from infinity to a particular point. Now potential at that point is due to these 2 charges. Potential at due to A and due to B. So you add in this way, you can find potential energy for a system of charges. This topic is also very important. It may ask in the exams. Okay, please take a screenshot. Then we will move to the next topic. Now next topic is potential energy of a dipole in a uniform electric field. Right? You know, when dipole is placed in a uniform electric field, what happens? It experiences some torque. We already discussed in chapter 1, right? And that torque is given by P cross E. It means PE sine theta, where P is dipole moment and this P is equal to Q into 2A. 2A is the distance between the two charges, right? Now, if the dipole is rotated through some small angle d theta, torque, it experiences torque, and if this dipole is rotated through a small angle d theta, then what happens? Small work done is there, and that small work done is given by, work done is what? Force into distance, but in rotational motion, in place of force you write torque, and distance here angular displacement d theta. So small work done dw is given by tau d theta. What is the value for tau? Pe sin theta d theta, equation number 1. Now this is the small work done in rotating through a small angle d theta. If dipole is rotated through from angle theta 1 to theta 2, then total work done in rotating the dipole from theta 1 to theta 2 is integration of this small amount of work done from theta 1 to theta 2. This is Pe sin theta d theta. You put the value of dw. It becomes, you take Pe outside, integration theta 1 to theta 2 sin theta d theta. Now what is the integration of sin theta? You know na, integration of sin theta is minus cos theta. Okay, so you just integrate this one, integration of sin theta minus cos theta, integration from theta 1 to theta 2. You take minus outside and put upper limit, then minus lower limit. It means minus P cos theta 2 minus cos theta 1. This is work done in rotating the dipole from angle theta 1 to angle theta 2. Now this work is stored as potential energy of this system, yani ki dipole, right? Two equal opposite charges, you know na, that work is stored in the system as potential energy. So potential energy is also equal to this work done minus P cos theta 2 minus cos theta 1. This is general expression for potential energy of a dipole in a uniform electric field, minus P cos theta 2 minus cos theta 1, right? Now suppose initially this dipole is at 90 degree, right? Theta 1 is at 90 degree and you rotate through angle theta. It means theta 2 becomes theta naught. What happens? Theta 2 you put in place of theta 2 theta and theta 1 90 degree, and you know cos 90 is what? 0. So it becomes minus P cos theta, or you can write minus P dot E. This is the expression for potential energy when dipole is placed in a uniform electric field and dipole is placed perpendicularly, and if it is rotated through angle theta, then that potential energy is given by minus Pe cos theta, right? Now there are different cases, special cases are there. First is position of stable equilibrium. Stable equilibrium is when it has minimum potential, and when it has minimum potential, when both electric field and dipole means both are in same direction, parallel to each other. Suppose this side minus q charge and this side plus q charge, and dipole is placed like this one. So dipole moment and electric field are in the same direction, right? Now theta is 0, and when theta is 0, cos 0 is 1, so u minimum becomes minus Pe. So this is the position of a stable equilibrium when potential is minimum, when both electric field and dipole moment are in the same direction, right? Next one is position of unstable equilibrium, means maximum potential energy. It is the case when both electric field and dipole are in opposite direction, they are anti-parallel to each other. Electric field is in this direction, and suppose dipole is placed like this one, minus q this side plus q this side. So dipole moment is in this direction, opposite to this one. Theta here is 180 degree, and you know cos 180 is minus 1, so u maximum becomes plus Pe. This is the position of unstable equilibrium when both electric field and dipole are anti-parallel to each other, right? Now position of zero energy. When energy is 0? When cos theta is 90 degree perpendicular to the electric field. So in this case u is 0. So these are different cases, and these two cases are very important, stable equilibrium and unstable equilibrium. When dipole, what is the position of a stable equilibrium? When theta is 0. What is the position of unstable equilibrium? When theta is 180 degree. In this way, you have to write all these things, right? Potential energy of a dipole in uniform electric field. First you write the expression for torque, then work done in rotating through a small angle d theta, then total work done from theta 1 to theta 2. In this way, this work is stored as potential energy. Now initially you take theta 1 90, theta 2 theta, you get the expression U equal to minus PE cos theta. It's very simple. Then different cases are there, okay? Hope you understood. Please take a screenshot. Then we will move to the next topic. So now up to this half part of the chapter is over, that is about electrostatic potential. Next half part is about capacitor, capacitance. And in this one, first I will discuss about conductor. What is conductor? What are different properties of conductor? Then we will discuss capacitor and capacitance, right? So first one is electrostatics of conductor. First, what is conductor and what is insulator? Conductor are those substances which conducts electricity, right now? And this substance has large number of free electrons or ions. They are charge carriers in case of conductors which conducts electricity. For example, metal, earth, human body, all are good conductor of electricity. Then insulator. Insulator is opposite to this conductor. Those substances which do not conduct electricity. No free charge carriers are there in case of insulators. Example, rubber, plastic, glass, wood, all these are example of insulator, right? Now there are different properties of conductor when conductor is placed in a electric field. First of all, most important property is net electric field. Inside a conductor is 0. Suppose this is a conductor, right? And there are large number of free charge carriers, okay? Large number of free charge carriers inside the conductor. But when it is placed in an electric field, suppose this is in this direction, electric field is there. So what happens inside the conductor? This negative charge comes towards this side, positive charge comes towards this side. Due to this, electric field is created here from this side to this side, and net electric field inside the conductor is always 0. Like this, we'll discuss in detail what happens when conductor is placed in a uniform electric field, when dielectric or insulator is placed in an electric field. So you just remember net electric field inside a conductor is always 0. Second, if electric field is 0, then net charge inside the conductor is also 0. Right now, according to Gauss law, if electric field is 0, then charge is also 0. So where the free charges are located in conductor? Where it is? Excess charge always resides on the surface of conductor. Inside the conductor, net charge is 0. So excess charge always resides, accumulates on the surface of conductor, right? Third one, electric field just outside the charged conductor is always normal to the surface of conductor. You know, electric field inside the conductor is 0. So electric field outside the conductor, suppose this is a conductor. So outside this conductor, electric field is always normal to this surface. This one is the point and normal to this one, right? Normal to this one, normal to this surface. Electric field just outside the charged conductor is always normal to the surface of conductor at every point, right? So this point is also very important. Just remember these things, because when we discuss about capacitor, all these things are required. Next one is electric field at the surface of charged conductor. What is the value for electric field at the surface of charged conductor? Inside the conductor, electric field is 0, but at the surface of the conductor, electric field is proportional to surface charge density, E equal to sigma by epsilon naught. If charge is negative, then you just E equal to minus negative surface charge density, right? So electric field at the surface of charged conductor is proportional to surface charge density, E equal to sigma by epsilon naught. And last point, electric potential throughout the volume of conductor, it means inside and outside the conductor, is constant. Constant means there is no change in potential. Inside the conductor, suppose this is a conductor, electric field is 0 and potential is always constant inside the conductor. And this conductor is used in many cases because of these properties. All these properties are very important. Most important property is inside the conductor electric field is 0 and potential is constant throughout the volume of conductor. Okay. Please take a screenshot. Then there is a small topic, electrostatic shielding. What is electrostatic shielding? Okay. Fast. Now there is a small topic, that is electrostatic shielding. It may come in 1 marks question. What is this? It is the process of protecting certain region from certain external electric field, right? If you want certain region where there is no electric effect, so that process of achieving certain region where there is no effect of external electric field is called electrostatic shielding, and it is achieved by enclosing that substance in a metallic chamber, because you know metallic chamber means conductor. Inside a conductor electric field is 0. You know na, there is no electric field inside the conductor. So if you want any substance to protect from external electric field, it's better you enclose that substance inside this metallic chamber or conducting body, so that electric field inside that substance is 0. And this process of achieving protecting the certain region or substance from external electric field is called electrostatic shielding. Application, let us see. During thunderstorm, you know it is safest to sit inside a car than near the tree outside the car. Why? Because the metallic body of that car acts as electrostatic shielding and it protects from lightning. There is no electric effect inside the car, so it is safest to sit inside the car during thunderstorm, right? Now second one, your house also acts as a hollow conductor, so there is no electrostatic effect inside the house also. This is very small topic. These are about electrostatic shielding. Please take a screenshot. Then we will move to the next topic, that is dielectric, then capacitor, capacitance, everything we will discuss. Okay. Next, dielectrics, non-conducting. We already discussed about conductor. They are conducting, they can conduct electricity, but dielectric are those substances which produce electric effect without conduction. It cannot conduct electricity, but when dielectric is subjected to an external electric field, in this one, charge induced on surface of dielectric. It is an insulator, but on the application of electric field, some charge induced on surface of dielectric light. So we will study dielectric when we talk about capacitor, right? It is very useful in that one. So you must know what is dielectric, and also there are 2 types of dielectric. One is polar dielectric, another one is non-polar dielectric. Polar dielectric is made up of polar atoms or molecules. What is polar atoms? In which center of positive charge and center of negative charge are separated by some distance. That atoms are called polar atoms or polar molecules. And if there is separation of charge, then it must have a permanent dipole moment, right? So polar dielectric is made up of polar atoms in which center of positive charge do not coincide with center of negative charge, right? It means it have permanent dipole moment. An example of this polar dielectric is HCl NH3 H2O. They have asymmetrical in shape. For example, H2O, size of O is different, size of H is different, so their centers do not coincide, right? They have asymmetrical in shape. That's why polar dielectrics have permanent dipole moment, because charges are separated. Now next, non-polar dielectric. It is made up of non-polar atoms or molecules in which center of positive charge coincide with the center of negative charge. And coincide means there is no separation of positive and negative charge. It means they do not have permanent dipole moment. They have temporary dipole moment, right? and center of positive charge and negative charge coincide means they both have same size. For example, H2. Here center of positive charge coincide with center of this negative charge. So they have asymmetric in shape, right? So it is very useful when we study about capacitor, capacitance. Then in that one dielectric is used, right? So dielectric are those substances which produce electric effect without any conduction, and there are two types of dielectric, polar and non-polar, right? Okay, please take a screenshot. Next, behavior of dielectric and conductor in an external electric field. What happens when conductor and dielectric is placed inside external electric field, when it is subjected to external electric field? Let us discuss one by one. First is conductor, right? Suppose this is a conductor, and when this conductor is placed or subjected to external electric field E0, this is the direction of external electric field. Now what happens due to this electric field? The negative charge inside the conductor moves towards this positive end, and positive charge moves towards this negative end. In this way, there is induced electric field inside this conductor, and direction of induced electric field is this one, right? So direction these charges moves unless and until it is this induced electric field is equal to external electric field, because inside the conductor charges can easily move. So in case of conductor, E0 is equal to E induced in opposite direction to that of external electric field. So E0 is equal to minus E induced, and when you add E0 plus E induced, this is equal to 0. It means net field inside the conductor is always 0. You know, inside the conductor there is no electric field. So in this way, when it is subjected to external electric field, then net electric field inside the conductor is always 0. You must remember this one, right? Now come to dielectric. What happens when this dielectric is subjected to external electric field in this direction? Positive charge is this side, negative is this one. Now inside the dielectric, charge carriers are tightly bonded, so there is very little amount of negative charge towards the positive plate and positive charge towards the negative plate. In this way, these charges are separated and induced EMF is produced, E induced, due to the separation of these charges. This separation of these charges, this process is called polarization, and due to separation there is a dipole moment, right? So polarization is nothing but dipole moment per unit volume, right? And this polarization increases when electric field increases. So this polarization is equal to chi E. Chi is called susceptibility of the medium. Okay. Now here what happens? E induced is not equal to the external electric field. This is always lesser than external electric field. It means there must be a difference of this external electric field to this one, E0 minus EI, and this is net electric field inside the dielectric. The main purpose of dielectric is to reduce external electric field by an amount, this one, EI. Right? So E0 minus EI is the net electric field inside the dielectric. But in case of conductor, net electric field is 0. Here, net electric field is E0 minus EI. Right? So these properties are very important. What happens when conductor and dielectric are subjected to external electric field? In case of conductor, net electric field is 0. In case of dielectric, there must be a reduced electric field. So by how much amount this electric field is reduced by the application of external electric field? That ratio is called dielectric constant. So one more thing, dielectric constant, right? Dielectric constant. When dielectric is subjected to external electric field, the electric field reduces. By how much amount this electric field reduce? So this dielectric constant is represented by K, and it is equal to E0 by E, where E0 is external electric field and E is reduced electric field due to application of dielectric in external electric field. So this is the formula for dielectric constant. It must be very useful when you are solving the numericals, and this dielectric constant is also equal to, in terms of capacitance, when we study after this one, this is equal to C by C0, where C is the capacitance in vacuum, in between the plates, vacuum is there, free space is there, and C0 is the capacitance when dielectric is introduced between the plates of the capacitor. So when dielectric is introduced, electric field is reduced inside the dielectric, but capacitance increases when dielectric is introduced between the plates of the capacitor. We'll discuss about capacitance after this topic, okay? So please take a screenshot. You must remember these properties about conductor and dielectric, right? Topic is capacitor, right? What is this capacitor? It is an arrangement of two conductors separated by some insulating medium or vacuum or free space, right? And it is used to store large amount of charge or electrical energy. Capacitor is an electronic component which is used to store large amount of charge and electrical energy. And how it is made? It is made up of two conductors. These two are conductors, right? Conductors, or you can say conducting plates, separated by some distance. In between these two plates, either free space is there or some any dielectric medium is placed between the two plates, right? So this is an arrangement of capacitor. Symbol for capacitor is, these two represents plates, right? And this is a symbol for fixed capacitor. If arrow is there, it represents symbol for variable capacitor, okay? Now, how much amount of charge this capacitor can store? That is called its capacitance. Ability to store large amount of charge, right? This is called capacitance. It is a measure of ability of a capacitor. How much charge any capacitor can store, that is called capacitance. Mathematically, the charge given to a conductor is directly proportional to increase in its potential. When some charge, suppose positive charge is given to this conductor, then there is an increase in potential difference between these two plates. So the charge given to a conductor is directly proportional to increase in its potential. It means Q equal to CV, and this C is called capacitance, right? Its SI unit is farad, and this C equal to Q by V. Q is in coulomb, V is in volt. So 1 farad equal to 1 coulomb by 1 volt, right? Now, this capacitance depends on shape and size of conductor. What type of conductor? What is the shape of this conductor? Where it is cylindrical shape, spherical shape, parallel, anything. Okay. So, the capacitance depends on shape and size of conductor and also nature of medium. What type of medium is between the two plates. So this is about capacitance, right? After this, we'll discuss different types of capacitor. Please take a screenshot. Next topic is types of capacitor. You already know what is capacitor, what is capacitance, right? Now there are different types of capacitor: parallel plate capacitor, spherical capacitor and cylindrical capacitor. It is not so important, but still you must know different types of capacitor. In case of parallel plate capacitor, two parallel plates are there, okay? Two parallel plates are there separated by some distance. These two are parallel plates, right? And this one is parallel plate capacitor. In case of a spherical capacitor, two spherical plates are there, right? In case of cylindrical capacitor, two plates, but these are of cylindrical shape, like this one, okay? this one, cylindrical shape, so cylindrical capacitor. Now next topic is capacitance of an isolated spherical conductor. Suppose there is a spherical conductor having some charge on the surface of this conductor. Let us suppose that plus q charge on the surface of this spherical conductor. Radius of this spherical conductor is suppose small a. What is the capacitance of this spherical conductor? How much charge it can store? Okay, so to find this one, first you know that potential energy at the surface of a sphere. Suppose this is a charge q is distributed over this surface of radius a. So how much is the potential energy at the surface of this sphere? It is equal to kq by r. Na? You know here r is small a, radius of the sphere. A is what? Radius of spherical conductor. Okay, and you know k is 1 by 4 pi epsilon naught q by a. Now from the definition of capacitance, C is q by v. Q, just put the value of v. V is 1 by 4 pi epsilon naught q by a. Just q cancel. You get 4 pi epsilon naught a. So capacitance of a spherical conductor of radius a, okay, is C equal to 4 pi epsilon naught a. So C is directly proportional to a. It means if the size of the spherical conductor increases, capacitance, storing capacity also increases, right? With the help of this formula, we can easily calculate capacitance of earth. Suppose this capital R is the radius of earth. So in place of a small a, you write capital R. So capacitance of the earth becomes 4 pi epsilon naught this R. I know radius of earth is 6400 kilometer. It means 6400 10 to the 6 meter. So this C equal to this K is what? 1 by 4 pi epsilon naught, and its value is 9 into 10 to the power 9. So from here 4 pi epsilon naught is what? 1 by K. It means 1 by 9 into 10 to the power 9. So you put the value, this 4 pi epsilon naught is 1 by K and this is 9 into 10 to the power 9. R is this one. You get the capacitance of the earth is approximate about 71 microfarad, right? So this is just a small discussion, not so important from examination point of view, but still you must know about these things. We discuss in detail about this parallel plate capacitor. What is the capacitance of this parallel plate capacitor? How much energy is stored in case of this parallel plate capacitor? What happens when dielectrics introduced? All topics are important about this one, parallel plate capacitor. So please take a screenshot of this one. Next very important topic is capacitance of a parallel plate capacitor. In case of parallel plate capacitor, what is its ability to store charge? That means you have to find capacitance of a parallel plate capacitor. This topic is very important, right? So to derive the expression for capacitance of parallel plate capacitor, consider two plates. Here one plate is charged, right, and other plate is earthed. It is connected to the earth so that extra charge flows to the earth. Earth is a good conductor of electricity, and these two plates are separated by some distance small d. Okay, now you know that due to a plane sheet, what is the value of electric field? E equal to sigma by 2 epsilon naught. So in between these two plates, due to induction process, what happened? Suppose positive charge is given to this plate. Now due to induction process, negative charge is induced towards this positive plate, and positive charge is this side, and this positive charge is connected to the earth, so it flows to the earth. Now one plate has positive charge, other plate has negative charge. It means electric field is set up between these two plates. And what is the value of this electric field? E equal to sigma by epsilon. You know, between the two plates, if the two plates have opposite charge, then electric field is this one. We already derived in chapter 1, right? So electric field between the plates is E equal to sigma by epsilon naught, where sigma is surface charge density and its value is sigma equal to Q by A, charge per unit area. A is the area of plates, both plates. These plates and these plates, both plate has A area of plates, right? Both plates have same area. Now, electric field, you know, sigma by epsilon naught, dot potential difference between the plates is how much? You know relation between electric field and potential, V equal to E into D. So, V equal to E sigma by epsilon naught into D. So, this V becomes sigma by epsilon naught D. Now, you put the value of this sigma, charge density, Q by A is the area of both plates. Then V becomes Q, in place of sigma you put Q by A. So QD by A epsilon naught. This is the value of potential difference between the plates. Now you have to find capacitance. So you know C equal to Q by V. Q by V. V is QD by A epsilon naught, right? Q cancel. It becomes A epsilon naught by D. So the capacitance of a parallel plate capacitor becomes C equal to A epsilon naught by D. From this formula, it's very clear that this capacitance depends on size of conductor. It means area of the plates, size of conductor, distance between the two plates, and also permittivity of the medium. So this is the formula for parallel plate capacitor capacitance, and it is very helpful when you are solving numerical. C equal to A epsilon naught by D. You must remember this one, right? After this, we will discuss what happens when any dielectric slab is placed between these two plates, right? Is the capacitance changed? By how much amount? In 1 marks question, it may ask what happens when dielectric slab is placed between the plates of a parallel plate capacitor. Answer is capacitance increases. We'll prove in this video, right? After this one, we'll prove how capacitance increases when dielectric slab is placed between the plates of a capacitor. Okay, first take a screenshot of this one. Now, next topic is capacitance of a parallel plate capacitor with dielectric slab between the plates. This topic is also very important. Please note down. What happens when a dielectric slab, suppose this is a dielectric slab, okay? Dielectric slab of some thickness T, suppose T is the thickness of dielectric slab, is introduced between these parallel plates, and these plates are separated by a distance D. Now what happens when this dielectric is introduced? Let us first suppose that sigma is surface charge density on these two plates. This is plus sigma charge density, this is minus sigma charge density, right? E naught is electric field between the plates when no dielectric slab is there. In vacuum, E naught is electric field between these two plates, and direction is from this positive charge to negative charge. This is direction of electric field in vacuum, E naught, right? Now due to induction process, what happened? Due to polarization, electric field is set up inside the dielectric. Opposite charges are induced towards this side, negative charge, because here is positive, and this side positive charge. So electric field is set up inside this dielectric EI in a direction opposite to that of E naught. So how much electric field is present inside the dielectric now? Because this E naught and EI are in opposite direction and they are not equal. So net electric field E inside dielectric is E naught minus EI, right? And also you know E naught is electric field between the plates in vacuum. It is given by sigma by epsilon naught, or sigma is what? Charge per unit area, Q by A epsilon naught. Okay, this is equation number 1. And electric field inside dielectric is E equal to E naught minus EI. And also you know how much electric field is reduced by the application of this dielectric, right? This is given by dielectric constant K equal to E naught by E. E naught is what? Electric field in vacuum. E is what? Electric field in dielectric, reduced electric field, and this E is E naught minus EI. So K is E naught by E. So this E becomes E naught minus EI becomes E naught by K. This is equation number 2, right? E naught is Q by A epsilon naught in vacuum, equation number 1, and equation number 2, electric field inside the dielectric becomes E naught minus EI is E naught by K, equation number 2. Let us suppose these distance between plates, A is area of each plate, T is thickness of dielectric slab. Now potential difference between the plates. Here electric field inside the dielectric is E and electric field outside this dielectric is E naught. So this electric field E acts over region T and this electric field E naught acts over region only in this space na? Before dielectric D region, but after application of dielectric of thickness T, this becomes D minus T thickness. This E naught acts over the region D minus T and E acts over region T. So total potential difference between the plates, you know V equal to ED. So here E is electric field inside a dielectric into thickness T plus E naught electric field in vacuum and it acts over the region D minus T. So total potential difference between the plates is ED plus E naught D minus T. Right? Now you put the value of this E is how much? E naught by K, right? And E naught you take common, D minus T 1 plus K. Now using equation 1, E naught is how much? Q by A epsilon naught. So this V becomes Q by A epsilon naught D minus T 1 plus K, equation number 3. Now you get the value of this potential difference between the plates after introduction of dielectric slab. Now what is capacitance? C equal to Q by V. So Q by V, put the value of V from equation 3, Q by A epsilon naught D minus T plus 1 by K, then this C becomes A epsilon naught D minus T 1 plus K. This is a general expression when dielectric slab of thickness T is introduced between the plates of a parallel plate capacitor. Okay, so it's very easy. You have to calculate C, it means Q by V. You just find the potential difference between the plates. And this potential difference is electric field into distance. So electric field in vacuum acts over the region D minus T and electric field in dielectric acts over region T. You just add, as potential is a scalar quantity, you just add these two quantities, you get the value of C. Okay. Please note down, take a screenshot, then we will discuss different cases of this capacitance. What? Okay, now I am going to rub this one. Please. Now, case 1. Case 1 is that suppose if more than one dielectric slab is placed between the plates. Now what happens when more than one dielectric slab is placed between the plates having thickness different T1, T2, T3, then capacitance C becomes, using this general expression, A epsilon naught by D minus, first suppose dielectric slab thickness T1, second has T2, third has T3. In this way you add, and also plus 1 by first dielectric slab has dielectric constant K1, second has suppose K2, third has suppose K3. In this way you write if more than one dielectric slab is introduced between the plates. Okay. Now case 2, what happens when dielectric fills entire space between the plates? In that case, when dielectric fills entire space. Entire space means in that case this T equal to D. D becomes T. Then capacitance C becomes how much when T equal to D? A epsilon naught by D. T is also D plus 1 by K. This D cancel. Then this becomes K A epsilon naught. Okay. So I have done something wrong here, I think. Okay, E naught acts over the thickness T. Sorry, I have forgotten. Here T is there. Okay, this T is there. T is here. So here also T1, T2, T3 in this way. Sorry, by mistake I have not written T here. You just add T here. Okay, because over the thickness T, this electric field acts. Okay, so here also Ka epsilon naught by, here T is there, so Ka epsilon naught by, sorry once again, A epsilon naught by D, and D is also this one, plus this T is also D by K. This D cancel, A K goes in the numerator and D here. Okay, so this is K A epsilon naught by D. Sorry, some mistake is there. Now it is okay. K A epsilon naught by D, and you know what is this? K A epsilon naught by D. You know capacitance of a parallel plate capacitor when no dielectric is filled in vacuum. C naught is given by A epsilon naught by D. So this term becomes capacitance in vacuum. Therefore, this C becomes K times C naught. Now it's clear that the capacitance when dielectric introduced between the plates increases by K times in vacuum. Right? Here capacitance increases when dielectric slab is introduced between the plates. Right? Okay, one more case is there. If dielectric slab is absent between the plates, then what happens? Okay, it means there is no dielectric slab. Thickness is 0. In that case, case 3, no dielectric slab between the plates. It means T equal to 0. In that case, C becomes C equal to, when this T is 0, this T is 0, these terms are 0. So this becomes A epsilon naught by D, and this is equal to C naught. Right? This is the expression when no dielectric slab is introduced between the plates. It means in vacuum, parallel plates capacitor, capacitance is A epsilon naught by D. And I am using that C naught here also. A epsilon naught by D, this one. So these are different cases. You must remember one thing, that when dielectric slab is introduced between the plates of a capacitor, capacitance increases by K times. From here, you can write dielectric constant in terms of C. Dielectric constant is K equal to C by C naught. C is capacitance with dielectric. Capacitance with dielectric. Here I have proved, right? And this one is capacitance when no dielectric, it means in vacuum, right? And from here it's clear that capacitance with dielectric increases when dielectric slab of constant K is introduced between the plates, and electric field decreases. Electric field is what? E equal to E naught by K. E. E naught is electric field in vacuum and E is reduced electric field in dielectric slab. So you must remember this thing, K equal to E naught by E equal to C by C naught. This formula is very, very important when you are solving numericals. K equal to E naught by E, C equal to C by C naught, right? Okay, please take a screenshot of this one. Then next important topic is energy stored in a capacitor. You know, capacitor is device to store charge and electrical energy. Then how much energy is stored by a parallel plate capacitor? You know, first to charge this capacitor, electric work is to be done by the charging battery, right? So how much work is given by the charging battery to charge this capacitor is stored in the capacitor in the form of electric potential energy. So amount of work done given by the charging battery to store charge in the plates of the capacitor is stored in the capacitor in the form of electric potential energy. I have written this one. The total amount of work done in charging a capacitor is stored in capacitor in the form of electric potential energy. First, suppose that plus Q charge is given to this plates, right? So potential difference between the plates is Q by C. Now suppose a small amount of, first suppose there is no charge and a small amount of charge dq is given to these plates. So a small amount of work done given by the charging battery is V into dq. This V is Q by C, so Q by C dq. Now total amount of work done in charging through plus Q charge. So integrate initially 0 charge, then finally plus Q charge is given to the capacitor. So integrate over this small dw. This dw is Q by C dq. And when you integrate 1 by C, you take outside, integration of Q dq. Integration of Q is Q square by 2, 0 to Q. Now you put upper limit and lower limit, you get Q square by 2C. And this work is just stored in capacitor in the form of electric potential energy. So you could write this becomes potential energy U equal to Q square by 2C. And you know Q equal to CV. So you put in place of QCV, you get half CV square. So this is energy stored in a capacitor, right? And this topic is also very, very important from examination point of view. Okay, so you must revise this one properly. After this, one topic is left, that is combination of capacitors. Please take a screenshot. Now next one is combination of capacitors. For this we will discuss series combination and parallel combination. If all the capacitors 1, 2 or 3 or n number of capacitors connected in this way, second plate of first capacitor is connected to first plate of second capacitor, then second plate of next capacitor is connected to first plate of that one. So in this way series combination is there. Okay, right? You must remember one thing, in case of series combination, charge is same on each plate, right? But potential is different for each capacitor. Okay, so net voltage V is divided on all the 3 plates. So V equal to V1 plus V2 plus V3. And you know V is what? Q by, suppose all the equivalent of all these 3, C1, C2 and C3 capacitance is suppose C equivalent. So this total voltage V is Q by C equivalent. V1 is Q by C1. V2 is Q by C2 and V3 is Q by C3. In this way you get the expression 1 by C equivalent equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus dash 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 n number of capacitors. So in case of series combination, you find from this expression that net capacitance decreases. Okay. Next one is parallel combination. If the first plate of each capacitor is connected to one point and second plate is connected to another point, this arrangement is parallel combination. Here again you remember one thing, potential difference for each plate is same, right? Between these 2 points potential is same. So for each plate C1, this second plate, this third plate, all has same potential difference, but charge is different for different plates. First plate has charge Q1, second has Q2, third has Q3. So total charge Q becomes Q1 plus Q2 plus Q3. You know Q is CV. Total equivalent of all these 3 capacitors, suppose C equivalent. So C equivalent V equal to charge on first plate is this one C1V. Charge on second plate is C2V. Charge on third plate is C3V. In this way you get C equivalent equal to C1 plus C2 plus C3. In this way total capacitance in case of this series combination increases. Sorry, in parallel combination increases and in series combination total capacitance decreases. Okay. I am doing fast revision because this video I think it become very lengthy. So that's why I have increased my speed. So I think after this no topic is left. Let me see. Now next one, a small topic is left, that is energy density. It may come in 1 mark question. What is this energy density? It is the amount of energy stored per unit volume of a capacitor. Suppose this is a capacitor, right, of area A and separation between the plates is D. So amount of energy stored per unit volume of this is the volume of this capacitor, right? So and this volume is area into this distance. So it is denoted by small d, energy per unit volume. Volume is what? Area into d. A is the area of the plate, d is separation between the plates, right? And energy, you know, energy stored in the capacitor is half CV square by A into d. Also, you know, in case of parallel plate capacitor, capacitance C is equal to A epsilon naught by D. You put this value in this equation 1, right? Then equation 1 becomes U equal to, in place of C, write A epsilon naught by D, V square by twice AD, A cancel. It becomes half epsilon naught V square by D square. And also, you know, E equal to V by D. So this V by D whole square, in place of this V by D, write E. So this is another form, half epsilon naught E square. This is energy density, energy stored per unit volume. Half epsilon naught V by D whole square or half epsilon naught E square. You must remember this one. I think in numerical also this formula is used, right? Again, one small thing, when two capacitors charged to different potential, one has potential V1 and this other is charged to potential V2 and connected by a connecting wire. Now, what is the common potential for these two capacitors? Both capacitor has capacitance C1, charge Q1 and potential V1, another has V2. Then common potential for this combination of two capacitors connected by a connecting wire is total charge by total capacitance. You know, na, V equal to Q by C. So total charge by total capacitance. Total charge is Q1 plus Q2. Total capacitance is C1 plus C2. And what is Q1? Q1 is C1 V1. What is Q2? C2 V2. So common potential, right, when two capacitor charged to different potential and connected by a wire is given by V equal to C1 V1 plus C2 V2 by C1 plus C2. Just remember this one, okay? Please take a screenshot of this one. So with this, I am going to end the class. I think this video, one shot revision of chapter 2 is very lengthy because this chapter is also very big, right? But no problem, I have covered each and every topic of this chapter, okay? If you want this type of videos for other chapters also, please write in the comment box so that I will make one shot revision for other chapters also. Okay students, till then keep revising and stay tuned with this channel. Thank you.